if I drew a picture kind of like this, and I put a tube over here, and I have maybe just another outlet that's over here, the big tube would be referred to as a standpipe. It's just a device inside of the reservoir. The standpipe is always connected to the primary hydraulic pump, whatever it might be, engine-driven, electric, whatever. But we'll call this our primary pump. And our auxiliary pump, whatever it might be, hand pump or electrically driven pump, we'll call this one the auxiliary pump. Right here. So the idea is this: when the level of fluid gets down to the standpipe, by nature the primary pump is going to be starved of hydraulic fluid. So the level gets down to here. Well, what that does for you by having the standpipe provides for the quantity of fluid that's beneath the level of the standpipe to be only available for the auxiliary pump. So we do this also, like for example, in some motorcycles. If you've got a valve that you can turn on the fuel tank in order to provide for reserve fuel, it does kind of the same thing. What it does is it allows you to drain from the tank from a lower section, so it provides for kind of the same idea. Understand too, the real purpose for a standpipe is another function as well. The primary function of a standpipe is to prevent contamination from entering into the primary pump. The particles will normally settle down to the bottom of the reservoir, maybe in sediment space, but again, an additional function of that standpipe is to provide for prevent contamination from getting into the primary pump. But we can use it for segregation of fluid. Another thing that we can do in order to segregate fluid would be to have staggered ports. If you look at the wall of the reservoir, you might find two ports that are located at different levels. These would be outlet ports that feed into a pump. Maybe one a little bit higher than the other. The outlet at the top is going to feed into a primary pump, and then once the level of fluid dips below this level, then the primary pump will be starved of hydraulic fluid, and then the level beneath it will be available to maybe an auxiliary pump. So that's another thing that we can do. Another way that we can kind of provide for maybe reserve fluid is just to have a partition in the reservoir. So you might have a wall that's been built up in the reservoir, and again, it does the same thing. One side of the wall feeds a power pump, the other side of the wall feeds an emergency pump. Years ago, I remember looking at the reservoir cavity for a brake system in an automobile. Now, they partition the reservoir, but for a specific reason. Why do you suppose they partition the reservoir maybe in that particular reservoir? Why do they do it? How come?
So to separate the systems so where one half of the brakes will still work if you end up with a rupture in the other half.
Good. Yeah, the idea is it provides for either front brakes or rear brakes in the event that one of the lines should break. So at least it retains the capability to have half of your braking system. So again, kind of the same idea. All right. So those are all different methods of kind of partition or at least segregating fluid. Something else. Many reservoirs may have a hand service port. In order to replenish the reservoir with fluid, you have to add fluid back into it. So they'll have a method for providing for hand servicing it. Might be a filler neck, might be a connection point for maybe a ground-operated pump that fills the reservoir back. A lot of the military reservoirs have, they've got an HSU that they use in order to serve the reservoir back up again. So it provides for a minimum of problems and contamination by servicing from a kind of a closed device. You may also find a device called a scupper. A scupper is kind of a capturing device for spillage of hydraulic fluid. It's a nautical term, and again, the idea is it's usually mounted around the filler neck. And again, if you spill a little bit of fluid, that collection of fluid goes into the scupper, and then the scupper drains to usually an overboard drain. Lastly, the finger, might be a device called a finger strainer. In the neck of the reservoir, filler neck, you may find a coarse screen. And it's not really a filter, it's more of a mesh type of device. The idea is it prevents gross contamination from getting in the reservoir. So again, if you open the reservoir cap up with the intent of servicing, and you maybe in an area where there's fodder or something that might get in the reservoir, hopefully that finger strainer will prevent gross contamination from getting in. Okay, so that's why it's there. Oh, also too, you may have a pressure fill port. Most commercial aircraft have the ability for pressure servicing the reservoir with fluid. The primary advantage of that is minimization of contamination, but it's also faster as well. The idea that you have to take a filler cap off and fill the reservoir back up again, you're opening the system up to some potential for contamination. But if you've got a pressure fill port, it provides the at least some method of kind of controlling contamination that could get into the fluid.
On that de-aeration plate, does it matter where the return fluid goes,
It'll
on
be
top
above
or
it.
below it?
Above it, yeah.
On top.
Indications for fluid quantity. There's a lot of different ways that we can monitor fluid quantity. And one thing, the simplest way would be just something like a dipstick, just like you have on an automobile engine, so we can verify the level of fluid at a certain point. Another way that we might measure liquid quantity or the level would be a sight gauge, and a simplistic version of that would be like a level eye. So you see that the fluid is to a certain point on the side of the wall of the reservoir. Another thing we might have is called a liquidometer. A liquidometer is a mechanical method of indicating fluid quantity. It works via a float. There's a float with an arm attached to it that rides on the level of the fluid. As the level changes, the float goes up and down. The force or the action is transmitted to a sector gear, to a pointer, and then it makes the needle go up and go down. But it's actually a trade name. If you were to look up the term liquidometer, it's actually, at one time it was a patented device for indicating fluid level, mostly used for fuel systems and aircraft, but it can be adapted to hydraulic quantity. So it just uses a float. I've got a kind of a crude picture of one that I'll show you in a minute. Additionally, attached to that liquidometer, you might find a device that works like a sender in a fuel tank, but it's for hydraulic applications. It uses a potentiometer, and as the resistance of the potentiometer changes, usually they use like a rod with a ring, and as the ring floats on the rod, it changes the position of fluid, or you can monitor fluid quantity that way by a change in resistance. Some hydraulic systems also have an electronic means by capacitance of determining fluid quantity. This is common more so for fuel in aircraft, because capacitances can vary, or at least quantity can vary based on density of fluid. So they prefer to use capacitance for indication of quantity. But we could do it by hydraulic methods as well. And if you've got a bootstrap reservoir, well, the reservoir fluid quantity could be indicated maybe by a piston position. And sometimes the piston, as it's moving, has got a calibrated scale attached to it, or there's a rod that bears against the piston that will indicate the fluid that's in the reservoir as a function of piston position. So it might have something like that. Many reservoirs, if they're a vented reservoir, they're going to have a vent. The application of force on the fluid is by atmospheric air pressure. So you have to have some push on the fluid, other than just maybe the column height of liquid going to the pump. So we have to have the exchange of air in and out of the reservoir. It prevents the reservoir from imploding. It also allows atmospheric air pressure to push directly on the fluid. Many of the vents contain a check valve. And if the aircraft should go into an unusual attitude, the check valve closes off to prevent spillage of hydraulic fluid out the vent opening. Some cases also, on some acrobatic aircraft, what they do with the reservoir vent line is they plumb it to the side of the wall of the reservoir. So they might have something like this for a reservoir. And here's the vent line coming out of it. But rather than install a check valve, they'll have a piece of tubing that just goes down the wall of the reservoir. For the brief period of time that the aircraft is transitioning, you might lose a little bit of the fluid. But ultimately, if the aircraft should be inverted completely, liquid seeps to some level, so you're not going to lose all of the fluid in the reservoir. Do you all kind of see that? All right. So they might have a vent line down the side of the reservoir. They may have a check valve. And again, the check, if it's installed, it works kind of like the vent caps that you find on batteries for aircraft. If the battery becomes tilted, the little lead weight kind of falls to the side, and what that does is it checks the flow of electrolyte, prevents you from losing it in the battery cells. Many reservoirs, if they're pressurized, will have a pressurization port. If they're pressurized by bleed air or some other method, you have to have a method for getting air into the reservoir. And if we're going to be servicing the reservoir, if there's already air pressure in the reservoir, there has to be a depressurization valve. And what that does for you is it allows you to be able to open the cap of the reservoir for servicing and not be sprayed with hydraulic fluid. So again, sometimes it's incorporated into the cap, sometimes it's a separate valve like a bleed valve, but it'll allow you to open the reservoir for servicing by hand and again, not be sprayed with fluid. Air bleed valves, some of the bootstrap reservoirs sometimes have a bubble of air that's trapped behind the piston, and we have to provide for a method of escape of that air bubble. So they've got a similar valve that they would use like for a depressurization valve that's attached to the reservoir, and it allows you to bleed out trace amounts of air that might be trapped behind the piston. And for bootstrap reservoirs too, since they're dependent upon system pressure for developing internal pressure in the reservoir, they may have a relief valve that they have it tied to the reservoir that prevents excessive pressure from building up. Many reservoirs also have an integral filter with a bypass valve. As a matter of fact, if you find a filter element inside of a reservoir, it will have a bypass valve. And that's important. We can't afford to stop the flow of hydraulic fluid even if it's dirty. We have to provide for some flow of hydraulic fluid to the pump, otherwise you starve the pump. So they'll have a bypass valve. One thing to remember is that that filter is filtering incoming fluid. It is, and that's the function of it. It doesn't filter fluid at the outlet to the pump. What it does is it filters fluid that has returned into the reservoir. If you want to verify that, you can take a look at the reservoir that we have out in the shop, and you can see that the return fluid is forced to circulate through the filter. So we don't put the filtration directly to the outlet of the pump. We filter the incoming fluid before it gets to the pump. Okay. And we might find a drain. Not all reservoirs have them, but many of them do. It provides the opportunity for removal of all of the hydraulic fluid, maybe for rinsing the sediment out of the bottom of it if it's been a buildup of sediment. Here's a cross-sectional view of a reservoir, so you can kind of see the component parts. This one's a vented reservoir, so it's got a vent attached up at the top, and it's got just a conventional method of adding fluid to it for servicing. You got a filler cap and a filler neck. There's a finger strainer mounted in the filler neck. There's a sight gauge mounted to the side of the reservoir. There are fins that are attached to the walls of the reservoir to prevent random fluid movement. Here's one of the return lines that goes to the reservoir. And again, here's baffles. The baffles, again, and fins kind of contribute to prevent random fluid movement. And there's a connection for the standpipe. The standpipe, of course, is always connected to the main system pump. And the very bottom of the reservoir, we've got the connection for the emergency system pump, whether it be maybe a hand pump or electrically driven. And that's all that we have. So, okay. Here's another reservoir from a really old book. This one uses staggered outlets on the one on the right. But again, the engine-driven pump is on the top, and the one for the hand pump is on the bottom. The reserve is really the difference in space between the two. And we've got some foaming space. There would be expansion space as well. And filler neck opening uses a sight glass, and this one has got a standpipe in it. So, okay. Another one, real old military picture. I think the FAA kind of copied that. But again, standpipe is connected to the normal system power pump. The reserve for the hand pump in this case is down at a lower level. The return line, oh, this is something kind of interesting too. They picture it coming in radially to the walls of the container. That isn't how it's done on many reservoirs. If you look at a lot of reservoirs, the way that they position one of the return ports or both of them, they come in tangent to the wall. So if I were to draw a circle that represents the cross section of the reservoir looking from the top down, the return line comes in at a tangent angle to the wall of the reservoir. And there's a purpose for that. The purpose is to allow hydraulic fluid to be exposed to the wall to get rid of what? Heat and air. That's right. So again, although they picture that the return line kind of coming in like a radial spoke of a wheel, it doesn't actually do that. But for clarity, I guess that's how they illustrate it in the picture. But again, for many of the reservoirs, the return line is tangent to the wall. All right, so what else? Okay, so here's a simplified view of what they show you in your new airframe book for a system. We can immediately pick out certain components that are on the reservoir. I didn't even talk about that. Sometimes you find even a sample valve that's incorporated on the reservoir. This provides for sampling of hydraulic fluid for analysis later. And you can see a standpipe. Standpipe connects to our engine-driven pump, and our alternating current motor pump must be the backup in this case, or it's supplied at the bottom of the reservoir with hydraulic fluid. This is a pressurized reservoir, and the air pressure enters into the top of the reservoir, but it has to be regulated. So many of these devices provide for regulation of air pressure going into the reservoir. This is a pressurization module. So we're pushing on the fluid in order to prevent cavitation of the pump. What else do we have in the circuit that's kind of interesting? We've got an additional heat exchanger. You can see that after the fluid gets to the pump, there's a couple of paths that the fluid can take. One of them, after the discharge of the pump, is going to be for the supply of normal system pressure. But there's another thing that we'll talk about later when we get into hydraulic pumps. Many of the pumps incorporated a port that provides for what they call a case drain. And it's for circulation of hydraulic fluid that eventually will return itself back to the reservoir. And they call that a case drain. Sometimes it'll go to a heat exchanger, but ultimately it ends up finding its way back to the reservoir. So, but anyway, this goes along kind of with the cooling circuit that they have in the hydraulic system. By the way, too, many heat exchangers for hydraulic fluid are mounted in the fuel cell of the aircraft. They're taking the natural advantage of cold hydraulic or cold fuel in order to aid in getting rid of the heat of hydraulic fluid. It's even done on military aircraft too. If you look at some really older aircraft like an F-4, they had a canister type heat exchanger for hydraulic fluid. The core of the heat exchanger contained tubing that contained hydraulic fluid, and the outer portion of it allowed for circulation of fuel. So again, what we're trying to do is we're trying to cool the fluid off as much as possible. Okay. Again, the purpose of reservoir baffles and fins. And I took several different sources to kind of give you an idea, but just remember when we get to the test, the purpose of baffles and fins, it prevents a random fluid movement. That's kind of what it kind of comes down to. So that's what we got. Temperature and quantity sensors. More often than not, the temperature indication is going to be in the return line of the reservoir. Again, that's going to be the hottest point that the fluid will be at before it's cooled off by the reservoir. And quantity indicator or quantity sensor might be there too. For down at the bottom of the slide, they show you what's called a liquidometer. And here's the float connected to a mechanical arm. And it's completely mechanical in operation. When the float moves up and down, the motion is transmitted to the arm assembly, and that allows a sector gear and a pinion to rotate, and that causes the needle to sweep across its scale. So completely mechanical. You have to have, it's a direct reading gauge. It can be modified by the use of a potentiometer to provide for remote indication of fluid quantity. But anytime you see the term liquidometer, it means it's mechanically actuated. So again, direct reading and no electric directly with this type of device. It's all mechanical. The P-3 aircraft, the Lockheed Orion, that used a liquidometer in it. Here's a picture of a P-3 reservoir. So here's the float connected to the arm assembly, and again, it goes directly to the gauge. So as the fluid level goes up and down, you can tell what quantity you have in the reservoir. And I found another picture of one somewhere. I don't know where the hell I got that from, but anyway, that's how they kind of do it. The float moves up and down. This one has in addition to it, it's got an electrical connector, but really it's a modification that it provides for remote reading. So we've got another indicator in the aircraft that senses fluid quantity via change in resistance. Fetid reservoir, this one came from a Bell helicopter, and again, you can see some of the components we've talked about. It's a vented reservoir, and we've got a filler neck, we've got a finger strainer inside of the filler neck. Here's the scupper that's mounted externally. It catches spillage, goes to an overboard drain. What else do we have? The vent, even though they don't show it, there's a filter element as part of the vent opening, so it's a vented reservoir. The hydraulic fluid is filtered, and again, it's return fluid that's coming back into the reservoir that goes through the element and then ultimately to the pump. So we have a bypass valve installed too. They label it as a relief valve. In the event that the filter becomes clogged, the dirty fluid can bypass the element, and we will be able to get fluid to the pump anyway. All right. And then, by the way, too, you'll really never know that the bypass valve is opened and you've got dirty fluid because, again, there's really no differential pressure indicator in that type of filter. So, but you won't really notice anything in the way of anything, but you will get fluid that goes to the pump. A different type of reservoir that I want to spend maybe just a bit of time on. Sometimes when I do the checkout in the shop, I'll take people over to the S2F mock-up and I'll have them look at the reservoir that they have mounted on that aircraft, on that trainer. It's a vented reservoir. Actually, there's two of them, but the primary reservoir has got a filter in the vent line. Okay, well, so it's a vented reservoir. So it prevents collapse of the reservoir if fluid leaves, and it prevents, the vent also allows for air pressure to get into the reservoir to push on the fluid. But you'll notice that they've installed a special type of check valve in parallel with the filter element. There's a reason why they did that. You have to understand that in the operation of the aircraft, if a lot of fluid is returning back to the reservoir, the air cavity that we have above that fluid would potentially be pressurized and would impede the flow of return fluid. So what we do is we install a check valve that allows air that would possibly be trapped in the reservoir an additional escape path. So rather than trying to get out by the filter that would act as a restriction, we provide a check valve that provides a go-around in order to be able to get air out that will allow a lot of fluid to enter back into the reservoir quickly. Do you all kind of see that? Yes or no? Good, because I'm going to ask you about that on a test coming up. Okay, so that's the purpose of it. The bypass check valve allows air to be expelled from the reservoir at a greater rate than normal when large volumes of fluid are returned to the reservoir and prevents unfiltered air from entering the reservoir. Hence, a check valve allows flow only in one direction. In this case, it's air. So air can pass through the filter, it's not a problem. However, when a lot of fluid is returning, that filter element acts as too much of a restriction for air leaving. So we need a path for air to get around the filter element to get out. Okay. Something else too. Reservoirs come in all different sizes, types, and volumes. But here's one from a 757 training manual to give you an idea. Total capacity for this has 3 independent hydraulic systems: a left, right, and a center. The total volume is 9.2 in this aircraft for gallons of hydraulic fluid, and in the center reservoir we got 6.5 or so. The volume above the standpipe, this would be the available volume to the primary pump, would be 6.6 gallons, and the center system 3.5. And then below the standpipe for emergency use, again, you got 1.2 gallons and the other 1.72. This has an air pressure relief valve. This also has a depressurization valve. If we want to vent the air pressure in the reservoir, if we're servicing it by hand, we can use the depressurization valve. It has a sampling valve located at the bottom of the reservoir. This is the outlet that goes to the engine-driven pump. It's got a sight gauge on the reservoir, fluid temperature transmitter mounted on it as well, a drain valve, quantity transmitter for remote indication of fluid, and sight gauge on it, and pressure switches. It provides a reading to the engine indicating and crew alerting system. They call it ICAS. So what that does is it provides for, it tells you if the reservoir pressurization is functioning normally. Simple reservoir. This one is a pressurized reservoir. Always pay heed to the placard that's on the reservoir. You may find information that's important for servicing on it. Sometimes they'll have multiple levels that indicate full quantity. And again, full means that it might be dependent upon actuator position. Again, you've got actuators that are unbalanced actuators. So depending upon actuator position, you may have different levels that may both indicate full as far as the reservoir is concerned. This is a DC-9 reservoir. It's a bootstrap reservoir. The smaller of the two housings contains the piston that the fluid sees for the hydraulic system. That force is transmitted to a larger piston that makes fluid available to the hydraulic pump.
Are the holes in the outside for cooling?
Cooling, yeah, cooling and lightening it, yeah. C-130, they've got multiple hydraulic systems aboard the aircraft. They use vented reservoirs. Oh, here's a good illustration too. Here's the filter housing for the vent line, but installed across it. I don't know if they can, you can't make it out on the tubing, but what you find is a check valve installed on the vent line that will bypass the filter element. And this is the booster hydraulic system, and they got another one that they call the utility hydraulic system. They're both vented reservoirs, but nevertheless, this is one method of retaining some redundancy in the hydraulic system. I think their flight controls are partitioned as well. One side of the system sees booster hydraulic pressure, the other one sees utility.
So on something like that flies pretty high, if it's a vented system.
Oh, okay, good question. C-130 kind of different. They've got electric booster pumps that they use before the fluid gets to the engine-driven pumps. That provides the initial push on the fluid. So, you know, every aircraft has done kind of a different deal or manufactured in order to prevent cavitation. The aircraft is pressurized, but they don't use air pressure on the fluid. They just elected to use hydraulic pump, a separate hydraulic pump to provide the initial push. Same thing is true kind of with the P-3 aircraft. No engine-driven hydraulic pumps on that aircraft at all. Even the Lockheed 188, the civilian model of aircraft, all electric hydraulic pumps. And again, there's a reason why they did that. You know, I'm sure that they came up with a rationale for it. There are no electric-driven pumps on that, hydraulic pumps on that airplane. Components that are kind of associated with a hydraulic system. Here's a pressure transmitter that'll go into our pressure manifold. We've got a filter check valve. Primer check valve. System drain connector, pressure relief valve. This would be for the return manifold, maybe. Return line filter. And again, this is it looks like a 2-gallon reservoir. Here's the scupper attached to the reservoir, and here's the piece of tubing that goes to the overboard drain. Okay. Placard on it. Better picture. Here's their suction booster pump. This is what initially puts the force on the fluid before it gets to the engine-driven pump. And control switch, or at least the panel for operating the electric fuel pump, electric hydraulic pump. This is what I'm going to require that you kind of know to and understand. There are basically 3 different things that will influence the level that you see in a reservoir. if you have actuators that are unbalanced, where you've got a piston on one side of the actuator and a rod on the other, the actuator position will determine the fluid level that you're going to see in the reservoir. Obviously, the displacement of that piston can change the level that you see in the reservoir. The difference in displacement from the actuator has to be accommodated by the reservoir. So if you push all the pistons out and the rod has been pushed out, the level, assuming you had a bunch of them, you know, the level's going to drop in the reservoir. And if you push all the pistons in, the rod occupies some of the level or some of the volume on the other side. So obviously that could influence the level you see in the reservoir. Another consideration for fluid level would be temperature. As the temperature of the fluid goes up, so will the level of fluid generally. And again, most hydraulic fluids are oil-based, so we can assume that you know, you're going to see some rise in the level if the fluid gets hot. That Condur reservoir that we have out in the shop, behind that temperature, or I should say behind that quantity indicator that's on the reservoir, you can see that it's been temperature compensated. So they provide a scale for temperature that will vary the level as the fluid goes up and down. The other thing that would potentially change the level in the reservoir for many systems would be the accumulator. And I put accumulator condition. The accumulator has the potential for holding a large volume of hydraulic fluid. It's a pressure storage tank. You can kind of think of it like a battery in an electrical system that stores energy. So when we, for example, if we use a hand pump in order to fill the accumulator full of fluid, well, the fluid had to come from somewhere. What it does is it takes fluid from the hand pump and then pushes it into the accumulator. So of course the level of fluid in the accumulator or level of fluid in the reservoir will drop. When you release the fluid from the accumulator, guess where it goes back to? It goes back into the reservoir. So again, if you charge the system with fluid under pressure, it'll cause the level of the reservoir to vary. The other thing that would cause the level of reservoir to vary would be another thing associated with the accumulator. There's a term called a flat accumulator. And what that means is the gas charge in the accumulator is gone. Just like a flat tire, when you've lost the gas or the air pressure in a tire or an inner tube. And what happens then is the entire sphere of the reservoir gets filled, of the accumulator gets filled with fluid. And there's nothing left to really push it back to the reservoir. So it'll cause the level of the reservoir to go down significantly. So one thing you want to do is you want to check before you service the reservoir back up. You want to verify that usually the accumulator has been has got the correct gas pressure in it, and you've not lost it. Because again, the volume in the reservoir is kind of contingent on having an operable accumulator. So if you lose the gas precharge, yeah, that'll cause the level in the reservoir to drop. Okay. Some complications in servicing reservoirs. If the aircraft is equipped with bootstrap reservoirs, servicing is somewhat of a problem because they don't have a cap on the reservoir itself that provides for servicing. Generally, with a lot of the bootstrap reservoirs, they service by means of a ground service cart or a pressurization device to fill the reservoir or service it back up again. A good example would be the L1011. It had 4 independent hydraulic systems and 4 bootstrap reservoirs. So you had to have a servicing cart in order to replenish the reservoir level when it gets low. So they don't have, it's not as easy as a typical vented reservoir where you just take the cap off, or even a pressurized reservoir where you can bleed the air pressure away and then open the cap up and service. This has to be serviced under pressure from a cart, a ground-operated cart. Here's the panel in the L1011 to kind of show you what you had to deal with. You plug the cart into any one of these 4 different circuits in order to service that particular reservoir with fluid. So again, kind of a hassle to do it. Here's a C-130. This is an Air Force operated C-130, and again, a little bit different for servicing the reservoir. Again, it might be as simple as just adding fluid into the reservoir itself directly from a container. Reservoir servicing, what I can tell you about this, pay attention to the placard. The placard tells you a lot of information, and read the service manual. You may have an indication for what's considered to be normal for reservoir operation, again, dependent upon conditions. For example, if you look at the reservoir that we have out in the shop for the Convair aircraft, that one says have landing gear down, speed brakes closed, hydraulic system pressure 0, and accumulator pre-charge present. And again, it sets up a baseline for establishing what level you should see in the reservoir. If the aircraft is configured any other way, the level of the reservoir may vary. So again, pay attention to the placard. On this one, I blew up the placard to kind of show you what it says. It says, number one, accumulator dump. That means that you don't have any retained hydraulic pressure that's in the accumulator. So you've bled off the pressure in the fluid pressure in the accumulator. The landing gear down and speed brakes are closed, obviously because that influences the displacement of fluid out of the actuators. They want the accumulator gas charge to be at about 1500 psi, plus or minus 50. And it says for hand fill, release the reservoir air pressure at dump valve. So what you do is before you open the filler cap up, since it's a air pressurized reservoir, we're going to dump the air pressure so we don't get sprayed in the face with fluid. And then lastly, it says before engine start, it says pressurize with air to 70 psi plus or minus 20. This is important to prevent cavitation of the pump. If you don't do this, you're going to possibly cavitate the pump, which means that it's very damaging to the pump. You already saw the video. And also there's no lubrication that's going to the pump because the hydraulic fluid provides the internal lubrication necessary to prevent it from burning itself up. They might have a pressurization valve that allows you to use a little bit of shop air. They do on Beechcraft aircraft. So if you've serviced the reservoir, one method of putting the air pressure back in the reservoir before you start is to they use air pressure from shop air in order to do it.
So on that, it says on the accumulator dump, you still have a pre-charge?
The pre-charge means the gas pressure that's in the accumulator. It's the initial push that is going to be available later on the fluid.
But on one accumulator, you dump it, it says you're dumping the pressure before you
You're dumping the fluid pressure, any pressure that's retained in it.
But the pre-charge is a different thing.
Pre-charge is a different thing. That's just the gas pressure.
Oh,
At
The
breakup.
other thing is exactly what's in the reservoir itself.
Yeah.
Okay.
So what you're doing is before you even use a pump, if there's a gas charge in the accumulator, the gas charge is always there. When you start the pump, you're pushing fluid into the accumulator to further compress that gas charge that you put into it. So now you're holding the fluid that's being delivered by the pump under the pressure of that gas. When you use an actuator, you're using the gas on that side of the diaphragm or bladder to push the fluid to the actuator. So when they talk about the pre-charge, that's really the gas pressure in the accumulator. The other pressure, the accumulator dumped, this means that if you shut the aircraft down and you haven't bled hydraulic pressure off from the accumulator, get rid of it. So operate an actuator until the fluid is all returned back to the reservoir. Okay, that's what it means. I'll bring in the mock-up from the shop to kind of demonstrate what that means. This is what they use in the field for servicing reservoirs sometimes. They use self-contained units that have integral pumps that, again, the intent is really to minimize contamination that gets into the reservoir. The servicing unit uses the container itself as a method for holding fluid that you're servicing with. So some of them have an integral pump, most of them do. This is an old military unit, but again, you can see it uses a gallon container of hydraulic fluid. This one is a commercial one. Again, it holds a quart container of phosphate ester-based fluid. Bootstrap reservoir servicing, again, kind of a problem. Again, you're going to have service under pressure. They don't have a cap on the reservoir that provides for adding fluid. What you have to do in servicing a bootstrap reservoir is push the piston back against back in the reservoir in order to fill it back up again. So sometimes even that bootstrap reservoir will have a spring in it that provides for the initial push on the fluid. So you have to have something that kind of overcomes the spring on one side of the piston in order to fill it back up again. These are old military pictures. Some aircraft in the 1970s used this type of hydraulic servicing unit for the reservoir, and you put a can of 5606 hydraulic fluid into a holder, and you clamp the top down, and it pierces the top and bottom of the can. The bottom of the can then serves as the entry point for hydraulic fluid that you can use with a hand pump to service the reservoir with. The pierce at the top works as a vent opening, so that now the fluid is actually provides for a vent of the can itself. And by intent, it pierces both ends of the can, so it prevents you from reusing the can for any other purpose. So again, that's why they did it. So, but anyway, it's an older HSU, hydraulic dispensing unit. The newer ones that were used by the military look like this. They had a capacity of about 3 gallons or so. And, I've seen one of them. The bottom portion of the device holds 2 gallons, and they cantilever a container up on top of it. And it's got a handle that, again, you close on top of the can, and it pierces the can so that you now have a vent opening for the can. And it's got an integral pump. It's even got a hose and a line attachment with a filter on it. I think it's a 3-micron filter or so. But in any event, it provides so that you don't contaminate the hydraulic system with contaminants. This is what they now use in the military for servicing a lot of fluids aboard aircraft. So it'll be either 83-282 or sometimes some transmission fluids, whatever they're servicing. But it's a modern version of the servicing unit that was previously used. So this one's for transmission fluid, but again, some of them are dedicated to hydraulic fluid. Right. This is a picture that I took years ago at the air show. I was coming out of the beer garden. I was staggering outside of the beer garden, and I happened to look upward. I was standing underneath an airplane. It was a B-52, and that's with the flap extended, and you can see the reservoir that they had in the aircraft. There's a filter assembly. Obviously, this thing is in service by hand. It's remote servicing for the reservoir. Maybe an electric pump that they have over here, I don't know. But anyway, this is the underside of a B-52 wing with the flap extended. Okay, fluids servicing. Again, a simplified schematic for servicing, sometimes from a hydraulic cart, sometimes by hand for servicing. Many of the Boeing and Airbus aircraft have an integral hand pump that they use for reservoir servicing. I'm going to show you a video in just a little bit on how it kind of works. And maybe I'll show you this now. This is the Citation Cessna. This one uses 87-257, another polyethylene-based hydraulic fluid. But let's take a look at this.
The hydraulic reservoir fluid level should be checked during pre-flight to ensure adequate hydraulic fluid is available for the operation of the landing gear and brake systems. The hydraulic reservoir is located on the forward pressure bulkhead. To access the reservoir, open the left nose baggage compartment door. Proper fluid level can be determined by visually checking for the presence of hydraulic fluid in the full and/or add sight glasses. To ensure an accurate fluid level check, the hydraulic accumulator pressure must first be bled off using the manual bleed valve located behind the hinged access panel and above the accumulator pressure gauge.
That's bleeding off
After releasing
hydraulic
the
fluid,
hydraulic
not
accumulator
gas pressure.
The actual fluid level can be determined. Refer to Chapter 12, Servicing of the Model 510 Maintenance Manual for procedures to service the hydraulic reservoir fluid and hydraulic accumulator pneumatic pressure.
Maybe another one. I don't know if this one is live or not. But,
What does the PRF stand for?
performance specification. They used to identify a lot of fluid just with an H identifier or an O even before that. Most of the specifications that to be more inclusive of characteristics of whatever they're talking about, they have a cataloging system for performance specification that's more definitive of a particular thing. So that's my understanding of it anyway. Of this one, is actually, no, this one doesn't work anymore. Anyway, so you can see a little bit about it. Something else too to remember, sometimes we can't bleed off all of the heat that we have in a circuit by virtue of the reservoir, so we have to have fin type heat exchangers mounted in the aircraft. The fluid is forced to circulate through a substantial distance in a tubing that gives you a lot of surface area. And in many cases, they buried the heat exchanger inside of the fuel cell of the aircraft. So here's one from a 737. This is from a P3 aircraft. Again, this would be mounted inside of the fuel cell of the aircraft. And from an A4 aircraft, again, they've got a canister type heat exchanger, and it allows hydraulic fluid to circulate through it, but also fuel is present as well. It will cool that hydraulic fluid off. So, Boeing 757, it cools the case drain of the hydraulic pump flow from the left, center, and right systems. And it looks like you've got a left and center heat exchangers in the left fuel tank, and the right system heat exchanger is mounted in the right fuel tank. And again, it's a fin type heat exchanger. There's a bit of information too. If you read the servicing instructions or the operations manual for the aircraft, they want to make sure that complete heat exchanger is immersed in fluid and fuel. If not, then you somewhat can damage the fluid. So you're going to have a minimum of about 600 gallons of fuel aboard the aircraft in order to keep that heat exchanger immersed in fuel.
Damage the fluid because it gets too hot?
It gets too hot, yeah. If it doesn't see the fuel, it just doesn't have any cooling capacity. Another fin type heat exchanger usually mounted in the fuel cell. Something else too to kind of consider, just using a little bit of troubleshooting information. You're doing some hydraulic fluid sampling, and you notice what you get back as a result after sampling. The hydraulic fluid is contaminated with fuel. Where do you suppose your leak might be? It's in the fuel tank. It's in the heat exchanger. It's very good. Okay. So that's what I can tell you about reservoirs. Any questions so far? All right. Let me show you a little bit of a video that covers servicing of a Boeing 757, and I think I've got a little bit also on Airbus too. So let me show you this real quick.
This program will demonstrate the procedures for servicing the hydraulic system on the Boeing 757. It will show servicing of the hydraulic system from the ground servicing panel using the manual hand pump and the pressure fill port. It will also cover the removal of hydraulic fluid in an overfull condition. Hydraulic servicing procedures are covered in Chapter 12, Section 12 of the Boeing Maintenance Manual. Consult this chapter for all applicable warnings and cautions. To service the hydraulic system, the aircraft must be in the following configuration: electrical power provided and the ground service bus energized, landing gear down and the landing gear doors closed,
Actuator position.
steering, and flight controls at neutral. And when servicing the right system, the brake accumulator pressure gauge must read a minimum of 2,500 psi. The ground servicing station is located in the aft left wing-to-body fairing. Releasing the latches will allow access. Servicing instructions are located on the door. The hydraulic service station panel contains a four-way, four-position valve and switch, a remote quantity indicator, a hand pump and suction hose, a ground part pressure fill port, and a filter unit. To check the three hydraulic reservoirs, rotate the selector valve first to the left system and observe the quantity on the remote indicator, then the center system and the right system. As indicated, the center hydraulic reservoir is low. To add hydraulic fluid to this system, move the selector valve to the center position. Remove the hand pump handle containing the suction hose from the stow brackets. Insert the pump handle into the pump. Wipe the end of the suction hose to remove any dirt, and insert the end of the suction hose into a container of hydraulic fluid. Boeing recommends BMS 3-11 Type 4 hydraulic fluid. Operate the hand pump. Observe the hydraulic quantity indicator at the servicing station and fill the reservoir until the full level is indicated. When the servicing is complete, remove the suction hose from the container and wipe any excess hydraulic fluid from the tube. Stow the suction hose in the pump handle and return it to its stowage bracket. Move the selector handle to off. To service the hydraulic system through the pressure fill port, proceed with the fluid level check as before. Set the selector valve to the reservoir to be filled. Remove the dust cap from the pressure fill port and wipe the fitting with a clean, dry cloth. Attach the pressure fill hose to the fitting. And service the system while monitoring the fluid level on the remote quantity gauge. Caution: do not exceed 150 psi fill pressure when servicing the hydraulic reservoir. Excessive pressure could damage the reservoir. When servicing is complete, remove the pressure fill hose and wipe the fitting with a clean, dry cloth. Replace the dust cap. Place the selector valve to the off position. Close the service access door. Proceed to the flight deck and perform a hydraulic fluid quantity check on ICAS. On the flight deck, close the ICAS circuit breakers on the P11 panel. With power provided to ICAS, press the electric hydraulic switch on the P61 ICAS maintenance panel. Check the hydraulic fluid quantities on the lower ICAS display. The quantity reading should be, for the left and right system, between 0.88 and 1.11. For the center system, between 0.93 and 1.07. This completes the servicing procedures for the hydraulic system on the Boeing 757. The following procedures are to be used to correct the hydraulic system overfull condition. Warning: care should be taken not to overfill the hydraulic reservoir. Overfilling can cause hydraulic fluid to enter the pneumatic ducting and the air conditioning pack, resulting in smoke and noxious fumes entering the flight deck and passenger cabin. Repeated hydraulic contamination of the pneumatic system can also result in damage to titanium ducts. After maintenance, a flight deck check of the hydraulic system has indicated an overfull condition on the right hydraulic system. This condition requires that hydraulic fluid be drained from the right system reservoir located in the right wheel well. To gain access to the right system reservoir, the wheel well doors will have to be opened. Warning: rapid action of doors may injure personnel or damage equipment if locks are not properly installed. Next, install the door safety pins. To drain fluid from the reservoir, remove the lock wire on the drain valve. Attach a drain hose to the valve. Bleed excess pressure from the reservoir. Open the drain valve and drain excess hydraulic fluid into a container. When the proper fluid level is reached, close the drain valve, remove the hose, and install new lock wire on the drain valve. With the draining operation complete, remove the door lock safety pins, and proceed to the flight deck to perform a fluid level check. On the flight deck, activate the ICAS display as before. Next, activate the ACMP for the left hydraulic system. Now, close the main landing gear doors, and then the nose gear door. With the landing gear doors closed, shut down the ACMP. Check the fluid levels on the electric hydraulic page of ICAS. If the levels are within the previously stated limits and all maintenance has been completed, return the aircraft to normal. This completes the procedures to correct an overfull condition on the Boeing 757 hydraulic system. This concludes the module on hydraulic servicing. It has covered the replenishment of hydraulic fluid and the removal of hydraulic fluid in an overfull condition.
Okay, I brought the trainer in from the shop to kind of talk to you a little bit about reservoirs. This only has one actuator on it. You can imagine if you have multiple actuators, it's gonna influence the level of the reservoir, depending upon which direction this piston has been pushed in. In this case, the piston has been pushed out, and we're displacing fluid into the actuator on one side, and what came out of it on the other side is gonna be returned back to the reservoir. But if you push the piston inboard, obviously there's a difference in displacement. And again, that will vary the level that you see inside of the reservoir. The other big thing that can kind of control the level that you see is that device, which is the accumulator. So right now, the level in the reservoir is right here, but if we use the hand pump, you all know that liquids are considered to be incompressible. If we allow the fluid from the reservoir to enter into the hand pump and push it out with a hand pump, it fills the accumulator up against the gas charge. This particular accumulator is a bladder type accumulator. There's a bladder inside of it, and on the bottom side of the bladder, you've got a charge of nitrogen. And it might be at 400 PSI or so. I'll discuss how we determine that actually is, what that is later. But there's a gas charge on the bottom of the accumulator. Right now, the system pressure gauge reads 0. So all you have is really slack fluid that's in the circuit that's available to enter into the accumulator. But when we operate the hand pump, the level of the fluid is going to drop because what it's doing is it's entering the accumulator, compressing the bladder and forcing the gas charge to be increased. So let's do this. So we get about 500 PSI in the circuit, and you can see the level of the reservoir has dropped. Where's that fluid? It's in the accumulator. So when we release that fluid from the accumulator to make the actuator work, the fluid is going to return back to the reservoir. So the gas charge now charged on the bottom of the accumulator is just forcing the fluid out under pressure. Okay, all right, okay. So again, the system could be at whatever capacity is for normal. Just understand if you've built up pressure in the hydraulic circuit, and there's an accumulator in that circuit, the accumulator can contain that fluid, right? The other thing too to remember as well, if you've lost the gas charge of the accumulator, the entire sphere of that accumulator will fill up with fluid. You may have whatever the system capacity is as being normal. It's just that a component has failed and it's holding that fluid in it, and it's giving you an erroneous reading on the reservoir. Okay? So far, so good? All right. Okay, I guess it's okay for a dinner break. I'll see you back at about 6:30.